branching algorithm, and this is a branching algorithm, an FPT branching algorithm, which is magic, literally magic. Okay. Okay. So what I am going to do is, so you will have an exercise after this. Okay, exercise will be to adapt this, and it is really adaptation. Okay, so we will do max leaf spanning tree. Remember, I was talking about yesterday. Input is G is a connected graph, K is an input. Question: does there exist a spanning tree with at least K leaves? I want to make a branching algorithm for this. Do you even see where to start?
So yesterday you was telling we can start with the spanning tree and then contour. So in the path we can say which one will become a leaf or root.
Okay. Even I can't remember. So I have worked out. I've told you, right? It's literally magic. Even if I told you algorithm, it's not very obvious that this is an FPT algorithm. Like D hitting said, there is no D to branch, right? Nothing. Patifa, if you want to say something, then say. Yes.
We can guess the root, and then if neighbors are greater than K, then we are done.
Yes.
So neighbors are less than K.
Okay.
Guess.
Okay.
Guess.
Okay.
And then repeat. Something like that.
Okay. Good. But do you realize? I mean, even if I try to, let's repeat, right? Doesn't seem where it will go. I mean, how do I analyze such algorithm?
At any time, if the leaves are greater than K, then we are done.
That's correct. So let's formalize whatever you said. Okay. So let me formalize whatever you said. So what I'm going to say, look, this is why I assume that this is a connected graph. Okay. Otherwise, whatever you are trying to say may not hold. You see what I'm saying? So what I'm going to say, G has K leaf tree if and only if G has K leaf spanning tree. Okay. So when I say tree, it may not be a spanning, but if you have something, right, like this, right, and you have lots of vertices here, and already it has a K leaf, then I can always complete it to a spanning tree with at least K leaves. How? Look, maybe there is some vertex here. Look, the graph is connected, so there is some vertex which is neighbor to him. Maybe this leaf is, so I add this edge. But then I have not decreased the number of leaves. Maybe I have sacrificed one leaf, but I have also got one leaf. So I can complete it. This is what I mean by G has k leaf tree if and only if G has k leaf spanning tree, because graph is connected, otherwise I cannot. So you are right, if at any point of time we get this, then we know we can complete it, so let us not worry about it, agreed. So this is very good. So this is what I meant, that let us formalize whatever you said, right. So okay, yes, and he also said guess root, okay, so I will guess root. Now what? I am just following you.
Degree has to be less than k.
Yeah, sure, all those things are fine. So like let's assume that all those base cases are taken care of this.
So guess the neighborhood.
Huh?
Guess the neighborhood in the span.
Okay, so what he is trying to tell us is that let's fix this root. Suppose this is the correct root, because we are guessing this root, so there are only n choices, right? If there exists a spanning tree with k leaves, there is one where I can fix this as a root, right? Some vertex I can fix, some internal vertex I can fix at a root, and I can guess that guy, right? So this is fine. So let's see, I'm not looking for any spanning tree, but we are looking for a spanning tree rooted at some particular vertex. Is there a spanning tree, is there a tree with k leaves rooted at R? Because you can go over all the R, so if I can answer this question, we will be able to answer this question, okay? So this is what mean by guess, okay? Now what he says, look, if I had k leaves here, then I am already done. Well, if it has k child, then I have already done, right? This is exactly what you said to me. Otherwise, let's guess which subset of this goes. Fine, I guess this. So I already would have spent roughly some 2 power k. I could roughly guess 2 power k in this. Now what should I do?
Now hopefully the measure is the number of, like this subtree has, measure should be like number of leaves in the subtree. It might not increase also.
So like, do you understand what I am saying today? If I tell you this is a correct algorithm, but it's just that you don't know how to analyze it. Like it's actually not entirely true, but okay. Let me give you a hint. Okay, we'll worry about this. If I tell you that if you chose a root correctly, chose root correctly, we'll prove in a much more general fashion, but let's just to get an intuition, like, and it's a very counterintuitive intuition, okay. So what, suppose you decided to pick root R, okay. So this is your root R, and suppose it has certain number of like neighbors. Suppose it has neighbors A, B, C, D, E, F. Suppose, okay. I claim to you there exists a spanning tree which contains these set of edges. All. There exists an optimum spanning tree. There exists a k leaf tree that contains these edges. Suppose if I am able to prove this, isn't this a great, what am I saying? If at all if there exists a k leaf tree, then there exists a k leaf tree which contains all these edges. So like in some sense I have partially created a tree. You see what I am saying, right? If I can prove this, if there exists a k leaf tree, then if there exists a k leaf tree rooted at R, then there exists a k leaf tree that contains all these edges. Then if I prove this, then what will I say? Okay, fine, take R, take all these edges, and then we will think what to do next later. You see what I am saying? But look, then what happens? I don't have to branch, right? I can just greedily take all this. You see what I am saying? If I fix the root, right, and I told you that if this is your correct choice of root, then look at all the edges, look at all the neighbors, right? Draw one edge each. There is a spanning tree, there is a tree containing these guys, and that will lead to k leaves if starting at root you had some way to get to a k leaf tree, right? Then I do not have to branch in all subsets, right? I just take all this, I said okay, grow this guy, because I know this can grow to a tree with k leaves, but we need to prove this, right? I mean it's not obvious.
You just look at the back edges, you can remove the parent edge and then replace it with the back edge to this side.
Everything is easy in retrospect. I didn't get it.
I'm just telling here, in the tree, that the k-leaf tree that we are looking at.
So are you trying to give me proof for this, or you are trying to give me proof for this? Is obvious. It's nothing big. It's actually obvious. What is not obvious is a statement. You see what I'm saying? What is not obvious is a statement. Proof is very obvious. And this is not good enough for us. We need much more general version of this lemma. But let's just, as this girl is saying, I will tell, okay, let's take among all the tree, how do you prove such things is very easy. So we'll prove something very formal, but let's try to do. Among all tree that contains R and has K leaves, take the one that maximizes F. Like it contains maximum number of edges from F. If it contained F, then we are already happy, right? So you have R, some set of edges because, and right? If some of its neighbors does not appear at all in this tree, that is easy to handle, right? If that vertex, some vertex does not, suppose A does not appear at all in this tree, then I can just add this, right? I am only increasing the number of leaves, I am not decreasing anything, right? So fine. So maybe, of course it is not here because, right? So maybe it is somewhere here, A, right? So this is an edge. What can I do? So I have introduced this edge, right? You can keep doing this, right? So I have got a tree with same or more number of leaves and it contains more edges from F than before, right? You understand my point? So this tells us a greedy way of growing my tree, right? You do not need to branch, right? Okay, so that's a idea number one, right? But I cannot prove this because when I am trying to grow this tree, I will have some partial tree at some point of time and I would like to grow that, right? So I need a lemma or theorem who generalizes this setting to a partially constructed tree and say look at any vertex and look at the people whom he doesn't see before, all of those guys could be included in my solution if at all I need to be, okay? So let me write it formally. Okay, so we need several things, right? So at any point of time, my algorithm will have, so this is how the algorithm will work, okay? At any point of time, my algorithm will have some root and some partially constructed tree, okay? And look at all the leaves of this particular tree, okay? Okay, these are, let's call these boundaries, okay? I would have already decided that some of you guys are already leaves, like you will never be, so these are either potential leaf or real leaf, right? Potential leaf or real leaf, real leaf. Real leaf cannot be extended, potential leaf could be extended. I need to prove that if I look at a potential leaf, if there exists an optimum solution where he is an internal node, then there exists a spanning tree containing all the unexplored vertices from here. Right? The way I said, hey, look at R, if R is an internal node, then there exists an optimal solution where all the edges incident to this are conducted. And here these are unexplored vertices. Already have constructed, say look at this guy and look at all the neighbors of this guy which are not yet considered. And I am telling you, if this vertex is going to be internal, then there exists an optimal solution where you can take all these edges into your tree. So then I can move my boundary further. What will increase, what will decrease, we do not know at this point of time. But this is my algorithm. At any point of time, I'll pick up potential leaf. I say, hey, are you a leaf, real leaf? Then I will branch. Yes, you are a real leaf. Then I convert into a real leaf, delete all the edges incident to him because, or you are not a leaf. So I am an internal vertex. If I am internal vertex, then I look at all unexplored edges, unexplored neighbors, and I add edges to them and grow my tree. What changed? Why will it stop? Those are different questions which we need to address, and we will address them. But that is an algorithm. Okay, there are several issues. Is the idea clear of the algorithm? Right? And why will we make progress? Look, the side where you made leaves, you will make progress. That is okay. If a vertex is potential leaf currently and has no neighbor outside, then you better make it leaf, no? He has no choice to grow anyway. So those guys are good. So every potential leaf has certain number of neighbors outside. Now notice what happens. Here he is not degree 0 for sure, because if it is degree 0 then you made it leaf as a rule. Suppose even if it has 2 neighbors, then I make him internal, but what I did, I made at least 2 potential leaves. So I have increased the potential leaf by 1. Okay, fine. The bad case is when it has exactly 1. Okay, that is a bad case, right?
But then you increase the number of vertices in the tree.
That is, n number of vertex could be n. So that cannot be your measure. Then that cannot be your measure because the number of vertex in the tree could be as bad as n. Okay. But now, look, if this guy I decided to be internal vertex and this guy is degree 2 guy, so can he be leaf? No, if this guy is decided leaf, then I can also make him a leaf, no? So I look at all his neighbors. Maybe he has exactly 1 neighbor, so follow him up because this guy is not supposed to be leaf. I follow him until I get 2 things. And if I follow him and I do not get degree 2, then this branching was not correct. And so you just follow this path. I will follow this path. Like, okay, my unique neighbor. Look at this guy, because if this guy has to be leaf, then there exists, I delete it, there is already a leaf here, right? So why should I stop here? I could have get a k leaf tree without him being a leaf. Okay, so I will follow this path, follow this path until he branches. Then I will gain something. And if I cannot, then this branch was just wrong. Okay, so let's formalize all this and let's try to prove the correctness of all this algorithm. It's counterintuitive. I mean, as much as you like to believe it's intuitive, it's extremely counterintuitive algorithm. Okay, so we will have the following set of things. We are given a root R. Okay, we are given a root R. At any point of time of my algorithm, I will have following things. Any branch, we have computed what? T, a tree in G, okay, containing R, of course. Secondly, I, the internal vertices of T, T, B, a subset of leaves of T, a subset of leaves of T from which T could be extended, and L, what do you call, these remains leaves forever, and X, the external vertices. all the vertices which doesn't appear in T. So we have some simple rules, okay. So what is some simple rules? Return what? At any point of time, mod L plus mod B is more than K, then what? Then I have got a tree with K leaves, and because of this I can just say yes. Okay. What is my second point? If B equal to 0, then what can you say? I cannot extend anymore, and like then return no. And third, what is this? If there exists V in B such that n of V intersection X is empty, right? If I have a B which could be extended but he has no extender, then what should you do? Move V to L, right? Move V to real F. So this is my some simple rules, okay. So what is my branching rule? Okay, so let me prove a lemma and then everything will, it's like very simple lemma. I call it branching lemma. Okay, if you read the paper you will be dead, okay. So don't even try to read this paper. I mean it's a 18-page paper like so suppose U is in B. Okay, so U is a vertex which can be extended, and there exists a tree T prime that extends T where U is an internal vertex of T prime, okay. Then there exists a K leaf tree T double prime, maybe I should say a K tree T prime, then there exists a K tree T double prime, okay. That extends so Vt vertex set of T union Ng of U, this is my vertex set, and what did I tell you? Et edges of T union what? Union U V. So U was here and U is in Ng of U intersection X or V, it should be V, that is it. So what does this tells us? It tells you that suppose I have a root R and I have a tree here, and suppose I have a vertex U, okay, suppose I have a vertex U here, okay, and there exists a K tree that extends this, like somehow extends this to T prime, okay, then I can extend T prime to T double prime by nothing but looking at all the neighbors of U and including this. This is what it tells. I can get another T double prime with same number of leaves, but I will use all the edges incident to U and unexplored vertices. This is what, right? UV, V is in NGU intersection X, right? So look at all the edges which are incident to this guy U, this is what. And how will the proof go? As before, there's nothing changed. It's just that I have made the statement formal, but the proof remains exactly the same. So look at your T prime. Okay, look at your T prime. Here is R, here is U. I don't know how it is. Okay. If there is some V which is not in this tree at all, this is your T prime, right? Right? So if there is some V which is not part of Vt prime, then what can I do? I can add this and add this. Great for us. Okay. Now notice, because this T prime extends this V has to be somewhere here, right? So either it could be somewhere here or it could be on the same path V. But in either case, I can add, suppose it is here, then I can add this edge and delete its parent edge, right? I have introduced this and this will contradict. Okay, if this is not how V is, right? V is one of his descendant, then I add this edge and I again remove this and I can add this edge. So what it is? I did nothing, but I proved my branching lemma that if there exists an optimum solution, then if I branch on U, then I can either decide to branch U is a leaf, then I gain something, or I can extend my tree by U and adding all those edges to my tree for those vertices which are not yet included in my Vt, but they are part of unexplored vertices. Okay, so this is what this lemma tells us, and this is a very simple proof. Okay. 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 So now let's write our follow path rule, and then we are done. This is branching lemma, and next let's call it follow path rule. Follow path rule or lemma, whatever. Okay, so what is a formal statement? Suppose again U is in B, and what is the case? Ng of U intersection X equal to 1. Okay, let Ng U intersection X equal to V. If there exists a K-leaf tree extending, if there exists a K-leaf tree extending, if there exists a K-leaf tree T prime extending T, okay, where U is internal vertex, this is important, vertex then there exists a K leaf tree T double prime extending T where both U and V are internal. Okay, so what does it say? It says to you, okay fine, here is my root, here is my U and it has single neighbor V. What is, suppose there exists a tree T prime, so this is T prime extends T, and what is the property of T prime? U is internal. U is internal in this tree. Then what does it says? Then you have another T double prime where both U and V are internal. Why? Suppose this is not true, then V is a leaf in this T prime, right? If T double prime does not exist, then in every K leaf tree where U is internal, V is a leaf, right? Where V is a leaf, then this is contradiction, because if I delete V, I still have a K leaf tree, because U has degree exactly 1 here. So that's it. So what does it tells us? It tells us that if I am trying to extend and I have just degree 1, so either I make him a leaf, or if I decide not to make him a leaf, then you keep going, there will be a solution somewhere. This is exactly what it says, right? Either I decide this vertex to decide that he is a leaf forever, that's correct, and if I decide that U is an internal vertex, then I extend it to his degree 1 vertex V, fine. Then I know because of this lemma, oh, if this is what is true, then actually there exists an optimal solution where both U and V are internal vertices. Great. So now you have to extend V. So either it has another degree 1, then you apply this lemma once more, or it has degree 2, guys, then you can apply branching lemma on that, right? So you can always do extensions, okay? And look, we are doing lots and lots of greedy everywhere, okay? So that's my end of my algorithm. That proves correctness of this algorithm. This algorithm is correct, but why is this algorithm an FPT algorithm? How do we prove it's an FPT algorithm? You get my question? This algorithm is correct, and it will, if there exists a K leaf tree starting at R, it will produce. But how do you analyze this algorithm? Nothing is changing. Like, is the question clear? Algorithm is very clear. We start at root, we look at a vertex, we either branch, either you are a leaf, then something would happen, or you are not a leaf. If you are not a leaf, then I will extend you because of this, or if you are a degree 1 guy, then I extend you using this. If you are a degree 0, then I would have made you to leaf anyway because of this. So I have taken care of degree 0, degree 1 and higher.
So at any point here during the algorithm, the number of leaves are less than k, and we are taking subset of only that. So it will be at most 2 per k, and there can be at most k steps, because in each branch you are choosing that this is a leaf, so your k is dropped by. Otherwise you are extending this, so ultimately you will get 1 leaf, so your k again drops by 1 leaf. So there will be 2 per k.
It will be?
Like approximately there will be k levels branching, and in each branch you will have 2 per k, because
So 2 power k square. So something like 2 power k square. This is not how you analyze, like this is very hand wavy argument. Can you come up with a real object and say, hey, look, this is dropping, that is dropping. How are we analyzing algorithm up until now? Not like what she said, hey, this happens in this. No, we had a concrete object and we said, when we are branching in this concrete object has dropped by something. When we branch in that, when in that direction, that concrete object has dropped, and hence the level is like, we had a way to argue. Otherwise, how will we prove correctness of this algorithm? If we are not able to associate something which drops, I cannot analyze this algorithm correctly. L plus B as a measure. In the beginning it is 0.
measure is k.
K minus number of
K
leaves.
minus a plus 1. K minus so initially it's 0.
So what happens if I use, so what you want to use? Tell.
K minus number of leaves. And whatever tree.
So let's say, because measure is not about beginning. Measure you have to associate to any instance which you get in the iteration of your algorithm. Measure shouldn't be just function of the input graph. Measure has to be function of any algorithm which you get. Look, it's a recursive algorithm, right? So I could get as, okay, a spanning tree, this partially constructed object. So my measure should be a function of what is the input is, right? Input is not just k. Input will be actually, so my input will be what? A tree, some L and some B, alright? And this is what my input is, some tree, L, B, this is what my input will be, right? So based on this I have to have some measure, right. So for example, and maybe some k or something, whatever, right. So your idea is let's use this as a measure, okay. Okay, fine, let's see what happens. So I have a vertex, I branch, right. So either this vertex becomes leaf, that's what you said, right. So either it becomes leaf or it becomes internal node, okay. So when it becomes leaf, side of L has increased by 1, do you agree? Set L will increase. So let's see, right. So I have to show that K minus L minus B, but how much, what has happened to B? B has dropped by 1. Look, L has increased by 1, B has dropped by 1, because how did you? Look at a border vertex, you branched on him, whether he is a leaf or he is not a leaf. So if you decide to put him in the leaf, the B set has decreased by 1. Do you get anything? Right? One guy dropped, one guy decreased. So it will be, wait, K minus L minus 1, no, plus 1, right, and this, so it will cancel out to be 0.
Degree should be at least greater than 1, right? If it's 1, we extend using the.
Yeah, no, I am only talking about the side where you made leaf. Side where you made leaf, you made no progress, you did nothing, in the side where you decided, this is where I am saying that, what you decided, okay, I put, look, my algorithm picks a vertex in B and decides whether I put it in the leaf or I try to extend, right, V, leaf or internal, means extend. We will come to this branch later, first let us fix this branch. So if I use your measure K minus L, I know what, at this point of time I had K, I had L, I had B, okay. At this point of time I still have K, right, so I still have K, good, and I have L plus 1 and B minus 1. So I have to show a change in measure here minus here, right, it should be positive. So here it is K minus L minus B minus of K minus mod L minus 1 plus mod B, am I doing correctly? No, minus B plus 1, okay. So it is K minus mod L minus mod B, right, minus 1 plus 1 gets cancelled, this is same thing, I will get 0. So no measure changed. So at least this cannot be. Someone wants to use K minus L, then we will have trouble here.
We add some data on it so that minus 2 and minus 3.
Yeah, I am not saying anything, and all I am just saying that whatever you suggested needs tweaking, that is all that I am saying, okay. I mean I can of course give you exactly right, then you will not understand why we use something and why we did not use something, right. So what is an issue with his measure? Look, somehow he is not able to capture the loss. Look, he did a great thing, he made someone leave and still he is not able to see the progress, right. He made a progress that, okay, I decided that you will be leave and still he is not able to see the progress, right. So I need to do some tweaking to my measure so that when I decide to make someone leave, I see some progress, right. And the other way, and to do that is like you give appropriate coefficients to these guys which will do the job for you, okay. Okay, so let us see, and look, okay, I'll come to that. So at least the one which worked for me is, let me write it down, I'll write mu is 2k minus 2l minus b or plus b, do I give plus b? No, minus b, this is it, and this is always greater than equal to 0 if you notice, okay. Now let us analyze with this measure, right, let us see what happens. So when you decided to put in leaf, what happened? Leaf increased by 1, B decreased by 1, but I have 2, I have 1. Okay? Okay. Okay. So let's write it down now. I have 2k minus 2 mod L minus B. Okay? I have to subtract 2k minus 2 mod L plus 2, right, because mod L plus 1, and minus 1. This is what I have to do. Let's see what is this. So look, it is minus 2k plus 2k. So this guy will get cancelled, right? This guy and this guy will get cancelled. I have minus 2l plus 2l minus 2l, this guy will get cancelled. So it is minus, like, and similarly this is minus p minus plus b minus p, this guy and this guy will cancel. What will be left? So from here everything will get cancelled. So what is this? Minus 2 minus, so plus 2, so at least decreases by 1, right? So at least mu decreased by 1 here. Okay. In the other side, what happens? Leaf remains leaf, right? Right? What happens? Here I have u, I have at least 2 vertices, then only I am branching, at least 2 vertices. So this guy moves to internal vertices, but at least 2 guys are added to B, more, right? So what happens? Here B increases by 1, because 1 you sacrificed and 1 you got. Okay, so let's see what is the measure here. So 2k minus 2l minus b, here minus 2k minus 2l and minus b plus 1, right? So minus 2k plus 2k will get cancelled, minus plus 2k, this guy will cancel, minus mod b and this minus plus b, this will cancel, this is minus 1 minus 1 plus 1. Okay, so mu dropped by 1 in both sides. So what is my running time of the algorithm? My running time of my algorithm is 2 to the power mu. And in the beginning, what is L? 0. What is B? Is 0, right? So this is upper less than equal to 2k. So this is 4 power k algorithm. All good?
You're also spending some time
On?
because you're doing 2 ways to get branches of one step, right?
No,
Aren't you guessing which are leaves, which are not leaves?
no. I pick a vertex in B, I decide, are you a leaf or are you not a leaf? I am not doing anything. I just pick a vertex in B and I decide, are you a leaf or are you not a leaf? I just branch on them. Arbitrarily pick a vertex. I am not doing anything else. Right? Because either it is every vertex, you just pick up a border vertex. Either he is an internal vertex in my original solution or he is a leaf. So I just branched on that 2 cases. Okay. So what is an exercise? This algorithm is for the undirected graph. What I want you to do, just to get used to this way of thinking, is to do directed max leaf spanning tree. So G is, say, okay, and here you are given not this but say R. From R every vertex is reachable, and what I mean this. it's an out tree. Okay, does there exist an out tree with at least k leaves? So this is called leaves. Okay, so I want directed version of this problem as an exercise. The same algorithm works. You just have to prove each lemma for this version, but actually each lemma will work. I just did it for undirected graph because it is easier to explain. Otherwise, like direction will go this, but that doesn't matter. Okay, good. Was it fun branching? It's a branching algorithm. Okay, let's do another branching algorithm. I have many in my list. Okay, this is slightly easier. Let's see how much you are able to digest. Okay, so this is called closure string. Please, better learn this algorithm because we will use it few times more when we will do p-tosses and do heavy randomization. Closure string. So what is your input? x1, x2, xk over some sigma, like over some alphabet sigma. I don't know what its size is, but it's over some alphabet sigma and a number d. Parameter is d. Question, and suppose each of this has length L. Okay, question, does there exist y in sigma to the power L such that Hamming distance between xi comma y is less than equal to d for all I. So this is also called center string. So what is the problem? You are given some string x1, x2, xk, and your job is to find a string y such that if you look at y and look at any xi, the Hamming distance means the number of places they differ at is bounded by d for all of them. Okay. Can you give me a factor 2 approximation for this? A simple factor 2 approximation for this problem? Huh? And why it is factor 2 approximation, madam?
There is one string which is more than 2k away, or whatever that is, 2d away. Then there cannot be one string which is d away from both these two strings. The one that I have picked and the one that's d away.
Is that okay? You didn't get it? So what she says, just pick up any string xi, and that's your factor 2 approximation. Why? Look at any other string, right? Suppose it is 2d away, strictly more than 2d away, then you cannot have a string who will be d away from both of them. So this is obvious. Okay. So then this is a very good case for making a p-toss, no? And we will make a p-toss using Fpt algorithm. But that will require heavy churn of bounds, so we will delay that for next week. Okay, but for now let us learn Fpt algorithm, and we will use that Fpt algorithm for p-toss. So it is important that we learn this algorithm. Okay. Okay, good. So let me rephrase this question a little bit. Okay, let me rephrase this. Okay, so I am going to give you some z and some L is less than equal to d. And my question is, does there exist a string y in the ball in L radius ball of Z? I will define what it means, okay, y such that Hamming distance between y and Z is at most L, okay. So this is what I mean. What do you mean by ball of radius Z? So look at any string which I can get from Z by changing at most L places, right. So any string which is at Hamming distance at most L is in this ball, like normally ball, okay. So question, does there exist a string y in this ball such that distance, Hamming distance between dh between y comma xi is less than equal to L for all I? Is the question clear? So now I gave you some string, okay, and I tell you, and I gave you a number L. I am saying, can you give me a string in this ball which is at distance at most L away from all these people? Do you get my point? Suppose I solve this problem, then I claim that we are done. So now I gave you a string Z and a number L, right. I am not asking, so this is my candidate center string, potential candidate center string, okay. I am saying, look, I am not interested in any center string, I am only interested in all those center string which in this ball, which can be obtained from Z by changing at most L places, right. So can you come up with y which is not too far away from the Z? Imagine I have a Z and I have this x1, x2, xt. I am saying, can you come up with y which is close to Z and also close to these guys? But I have given you, give me y which is close to Z, right. So first of all, how do I pick up such a Z so that if I find something here, then I will find something here? It's not very clear. But suppose if I can solve this problem, then can we solve our problem? Look, this is why I asked you, can you give me a factor 2 approximation? And everybody said, yeah, this is fine. So what will I do? Imagine, I will take Z equal to x1, I could have taken any, L equal to D. Now if there exists a string, center string y, then clearly that is in this Hamming distance, and clearly, so if I can solve this problem, then I can substitute Z equal to x1, L equal to D, and we will be good. So all we need to do is to solve this problem. Do we agree to this? Okay, fine. Okay, now please give me a solution to this problem. It is easy. Please ask a question. If Z is not a solution, then what? And then what can you do? Okay, so question. If Z is not a solution, then what? Then what can you say? Like if I just check, is Z close to all xi? If it is, then I just output you Z, right? If it is not, then what? Then as a contrapositive, what can we say? There exists a string, okay? There exists a string xi such that Hamming distance between xi and Z is more than L, because we had given a parameter L here. Agreed? Okay, fine. What is the meaning of this? So let's pick up, look at this xi and this is Z. So pick up any L plus 1 position. This is L plus 1. They could differ at many places, but I just arbitrarily pick L plus 1 position. What can you say? If you are looking for an y whose Hamming distance is at most L, it better be equal to one of these positions, right? The potential y which I am looking, his Hamming distance from this is at most L. It means at one of these places he must be same as my string xi. So that leads to me how much? So what is my algorithm? I will do L plus 1 way branching, right? What is that? I take what is my, I call center Z replace some xi, replace some xi, zi replaced with some xi, blah blah blah. I mean, I'm not writing it completely correct. Okay, and what is my new parameter? L minus 1, because from Z I have gone to another string which is Hamming distance. So first of all, what is the branching factor? L plus 1. And what is the branching depth? L. Okay. So this is basically L plus 1 to the power L algorithm. Agreed? And since you all agreed, this is basically order d to the power d algorithm. Right? And we will show that this is optimal. We cannot do better than d power d. We will show. Later we will show this is optimal. Okay? Okay. So this is a good opportunity to introduce Fpt approximation. Okay? So let me do that. So what is my goal? I will call, okay, so my problem remains the same, but my question changes. So problem, say APX closest string, okay, input is whatever it is, I also give me epsilon, you give me epsilon, okay, my parameter is k and epsilon, but what do you have to output? Question, if there exists a string y such that Hamming distance between each xi and y is at most d, then you can output y star such that Hamming distance between xi and y star is at most 1 plus epsilon times d. So if I say no, I cannot output, it means that the Hamming distance, like there is no center string with Hamming distance at most d. But if I give you 1 plus epsilon times Hamming distance, that doesn't mean that there exists a string with Hamming distance at most d. You understand? When I say no, I am clearly correct. There is no Hamming distance. But if I give you string, that doesn't mean that there exists a string with, there exists a center string with Hamming distance at most d. Okay. Now I will do the same algorithm. Okay. But now what is the property of Z? Z is a property, does there exist a string y in this? Now what should be my L? Right? So let's call this L star. So this is what I will guarantee. L star, L star. Okay? Do you get my point? So now I want to maintain an invariant that, look, give me Z, some string Z, all I am allowed to do is output me 1 plus epsilon times L, and L is between 1 to d. And if I can do this algorithm correctly, whatever the running time will be, I can do as before. But now let's look at the trick. Okay, fine. Why then, what can I say? There exists a xi in Z which is more than 1 plus epsilon times L. Agreed? Here I have to say something. Okay, I shouldn't say does there exist. If there exists a string y which is in the, look, I have to put in this framework, right? If there exists y such that the Hamming distance is at most L, then you can produce this, okay? If there exists a string y such that let's like, okay, I'll tell you. So this is how the definition of ball is, okay? If there exists a string y in this such that this happens, then you can output y star such that for all I, Hamming distance between xi and y star is at most 1 plus epsilon times, just the prerequisite like this. Okay. And again my xi will work, because if there exists a solution, then xi itself is one such candidate, so that for every one this happens. Okay. But now look at what beautiful things happens. So why Z is not a candidate solution? Because if Z itself was a candidate solution, I would be happy, because there is some string which is 1 plus epsilon L. But what we know, that in the ball of Z there is some string which differs at most at L places. So this Z guy should match with him at how many places? There are like that center string, that real center string which exists, right? Look, there exists, or if there exists a real center string y, then y differs at how many places, or y should be similar to xi on how many places? Epsilon time L places. How many time places? Epsilon time L places. So now what I will do, randomly pick one of the positions. What is the probability that I would have succeeded in picking this epsilon L places where it should be same, right? It should be, look, how many positions are there? 1 plus epsilon L positions are there. How many of them are good position? Epsilon L are good position, right? So with probability, like if you choose epsilon correctly, it is epsilon by 2. With probability epsilon by 2, I will succeed in, look, there are many more places where I should be equal, right? So I just randomly chose epsilon L position, like one position, and I flipped it. So I would be correct, probability that I will be correct in epsilon L places I should be same as this string, and total number of places where I differ is this, so it is epsilon by 2. Like you can show epsilon by 1 plus epsilon is more than epsilon by 2, because look, what is 2 epsilon? It should be greater than or equal to epsilon plus epsilon square. If epsilon is less than 1, then this is, epsilon is always less than epsilon square. So this is fine. But what is the running time of this algorithm then? Right? So this algorithm runs in polynomial time, right? But what is the success probability? Success probability of this algorithm is to the power L, right? So the running time of this algorithm will be actually D. But so I can get close to this using this algorithm. So what is this algorithm tells us? That look, if I have a center string which is close to my all the strings, then I can produce a string which is not too far away, right, in time proportional to 1 over epsilon. So for example, if you wanted 1.1 approximation, right, then this is C power D algorithm, right? It is like fixed constant to the power D algorithm, right? So yes?
I didn't understand this. Why should be equal to xi in epsilon in places? Why?
Look, if I have a real string, what is the promise given to me? Promise given to me, there is a string which differs from all the string only at L places. Okay, fine. Now this string differs from this at how many places? 1 plus epsilon L places. Z differs at this at what? Epsilon L plus L places. It means that the real string has to be equal at epsilon L of these places.
Equal with
Z. So then this is why I flip.
Not equal with xi then, equal with z.
No, equal with xi.
Z differs.
Look at y. Y only differs from xi at L places.
Oh, this epsilon. Right.
Yeah. So like I'm trying to get closer to this y, and this z is differing from this guy at epsilon L plus this. So this guy can only be allowed to be this at epsilon L places. He must be same. I don't know which one of them this, so I just randomly pick one of them. Okay. It's a cool random. We'll get back to it with more details when we'll do p-test. But I just wanted to give you that the same algorithm. Look, Fpt algorithm is not very hard. Like I just choose d plus 1 places. One of the places must be similar. So I branch and I flip it to be equal to this place and do stuff. इन लोगों ने हमारा चाय कॉफी नहीं लाया ना? Just wait. Is there a phone here?
Yeah, it's
Do you know the number of canteen?
canteen.
Can you call them that I requested them for tea coffee to this Balaji?
It's 3 o'clock, right, sir?
3:15. Just call them, no?
Okay.
3:20. Okay, I'll keep
I
teaching.
don't know the canteen number. I will ask them. Tell you.
RK Balaji.
Yeah, I will ask him.
Okay. Okay. So we managed to do closest string. So what more I would like to teach is, I don't know whether I will teach today or tomorrow, is LP based branching. Dominating set in D-degenerate graphs and split vertex deletion as fast as vertex cover. So these three things were on my agenda. I don't think
Another 5 minutes.
he will come. Okay. Okay. We'll do one of them. So which one should we do? This we cannot do. This is too much. Like it's a 1.5 hour in itself. I mean, it requires patience, like carefully doing it with surplus and all these things. So, should we try to do dominating set in D-degenerate graph? It's not obvious that you can branch. You know dominating set problem. And what is the property of D-degenerate graph? So in turn, it implies that naive, right? That maybe we should branch on this, no? Because either this vertex will go into the solution or one of its neighbors will go into the solution. But we get into trouble very soon, right? So if you start looking at this, you will start to get some set of objects. Okay. So at any point of time you will have a set Y, which is like inside dominating set. You have made a decision, right? And there will be some vertices which already dominated. Okay. let us call this B dominated. At any point of time when we do branching or whatever it is, these are the state of my algorithm. Some vertices are part of my dominating set, some vertices are already dominated because they are neighbor to y, and some vertices are yet to be dominated, right. If somehow I could guarantee that all the time I can find a vertex here whose degree is small, then I could branch. What I mean by this, if I could say that, hey, there exists a vertex V who has degree at most D here, right, then that's great. Either this vertex will go into the solution or this vertex will go into the solution, this, and we can accordingly change these partitions. But it is not clear that even if I look at the graph induced on this, maybe the small degree vertex is here, which is already dominated. So I cannot guarantee a small degree vertex all the time which is undominated, because if I could, then I could just make progress, like branch on that and I can make progress. But it could happen. You get my point?
Since it's a small degree vertex, it will dominate less vertices.
What do you mean? I am going to branch. Look at a vertex which has 3 neighbors. You need to pick one of these vertices into your solution. Whatever it may happen, a dominating set must contain either this vertex or one of its neighbors, right. So the problem is that the small degree vertex could be here and that guy is already dominated. So I mean I cannot say that either you or one of you will go into the solution, okay. So we just play some tricks here. I partition this vertex set into, I call it B high, B low, okay. And what is its degree? D plus 1 less than equal to D, okay. And what is W high is the following, okay. This is very important. Vertices that have neighbor in BH or in W. You get my point? Maybe there is a vertex here with neighbor, then I will put it here. So what is left here? These are the vertices which are not neighbor to this and they have no neighbors in WH. So basically this is an independent set, right. What I do? Look, first of all I take all the neighbors of these guys, okay. I take all the, then I look at, okay fine, is there any vertex which has a neighbor already here, then I take that vertex and everything else. I just keep doing this. So WH vertices that have neighbors in BH or in W, right. So what is WL? It's an independent set, because if it had a neighbor somewhere, if it had a neighbor here, then I would have placed in there. If it had a neighbor here, then also I would have placed it. The only place this guy has a neighbors is to BL. Agreed? Okay, invariant. So these are some invariant which I will maintain. Okay, so here is a very beautiful cute trick, okay, extremely cute trick. Okay, so invariant, let's write it down. It's very important that we write down the correct invariant, okay. Look, here also no measure, nothing is clear, okay, nothing is clear, okay, and we have to branch. So we have to be very careful in life, okay. Okay, look, let's take H equal to graph induced on BH union WH. What is this graph? It's also D degenerate graph now, and it should have vertex of degree at most D. H is D degenerate, and hence there exists a vertex V in H such that degree of V in H is at most D. Where is that vertex? Right? So whenever I say so then to say that I should say that this guy's degree is D plus 1 in WH, otherwise we cannot say this. So clearly now V is sitting here. So this is very clear that V has at most D neighbor where? Here, here, here or here. But this guy could have unbounded neighbor here. I cannot help it. Do you agree? How can I branch on him then? Can I branch? And if I branch on him, what will I make progress? Do you get my point? Look, I would like to branch on him, right? Very nice, right? So I can say either I take you in my solution, or I take all these BH guys in my solution, or I take these WH guys. That is at most D, very happy. But hey, they could also be dominated by these guys.
The PL guys are responsible for dominating the W. PL or the WL guys are responsible for dominating the WL guys, but they are independent.
I mean,
WL is independent.
no, come again.
WL is independent.
Yes.
So WL has to be dominated by WL itself or BL.
Yes.
So when I'm branching on V, even if it has a lot of neighbors in BL, can I postpone this decision of taking them because they have to be taken because of WL?
But I have to quantify. Yeah, I have to quantify. How do I quantify?
Can't be this,
Yes.
can't be this for WL, right? Rather than picking WL, picking neighborhood of WL and BL. So we can do that. After that, we can branch.
No, I don't get what you said.
No, I'm telling WL is an independent set.
Yes.
So rather than picking them to dominate themselves, we can pick the neighborhood of WL intersection B. We can pick that into a solution.
Why?
Because otherwise, picking WL itself it doesn't help to dominate anything else. At least picking BL will help dominate.
How many BL do I pick? I mean, but maybe these guys, I need even a smaller number, no? I mean, look, it's like you cannot just do greedy. Maybe I need some subset of subset of BL to take care of all WL. I mean, I just don't know. Like, you understand my question? I just greedily cannot go and pick anything I like. You guys are missing something. So, no. So, okay, so let me give you a hint. I want to branch on this V.
Create this a separate set and keep this BL like this.
चाय पिलाओगे क्या भाई? कहाँ आ रहा है? आ गया? 5 मिनट और आ जाओ. And learn to quantify. I mean, keep a set this. No. I want my measure to decrease. Otherwise, I cannot prove that this algorithm is correct. This is an important point. This is all that I am trying to harness from that point of time. Okay. From WL, how many people can we pick? From WL, how many vertex can be picked? Huh? How many? At most, how many vertex can you pick from WL? Sorry, not WL, BL. Yeah, so at most K. How many guys can they dominate? So you can't quantify that. If I add too many people, oh, so like I can branch, right? Either all of you or please let me be dominated by that guy. If that number increases too much, then I have to say, forget it, you cannot branch on that. You understand my point? Look, if the number of people who BL has to be responsible for is too many, the guy cannot be responsible then. So how do you quantify that responsibility? Look, yeah, I want to branch. I want to say, look at this V guy. Hey, either I go into the solution, or you go into the solution, or you go into the solution, or you go into the solution, you go into the solution, you go into the solution, or I being dominated by this guy. Right. So you made him this, like you said, I don't know, please let BL take care of me. But how many people BL can take care of? KD. So if I give him responsibility for too many people, the guy will die. So quantify that, no? You get my point? You get my point, right? This is it. There's nothing, I mean, I'm not doing anything fancy, right? But this is what you have to understand. And like when we were doing kernelization, this is exactly what we were trying to do. So I'm just trying to make that as an algorithm. So now, can I write this lemma? If at any point of time, WL, number of people that you need to be responsible for, is more than D times K minus Y, then say no. Look, this is WL, these guys needs to be taken care either by themselves or by them. So if they themselves can take care of only one person, so if this is too many, then no. We'll worry about this, how will we take care of this? That's a very different question altogether. I'm not even talking about that. But if this number is too much, then we are dead. Okay. So our bottom case will be when the BH and WH will be empty set. Okay. So now let's branch on this V. So what is the meaning of branching on V? Okay. So branch on V. Okay. V is in Y, your solution, and suppose it has neighbors, say x1 to xd. Either x1 is in Y, x2 is in, Y, x d is in Y, some, right? So this is how many branches? D plus 1 branches. Either I go into the solution or this. And last, D plus 2th branch, what will I say? Please take care of me by BL. And how will I force that? How will I make sure that that happens? Okay, I will delete all the edges incident to me except to BL, and then I will make myself independent set and move to WL, right? Which is same as move V to WL by deleting all edges incident to V but to BL, right? I am made him. So WL size has increased, right? So that then we can quantify WL, no? WL cannot be too many. So what is my measure? What should be my measure? Now that I have told everything, there is nothing left. we have still not handled bottom case. Okay. So whenever BH union WH is non-empty, we branch, right? Because then we can look at this graph, we can find this vertex, and we can do this, right? And when you put V in Y, you take all its neighbors to this, you do all these kind of things whichever is required to do, like you redo everything with smaller parameter. But what is my measure? You tell me, what is my measure? What should be my measure? It's very simple, no? That's it. Right? So in one side, what happens? In one side, in all the D plus 1 branches, right, what happens? Mod Y increases by 1. Okay? So mod Y increases by 1 and WL nothing happens. Okay? So what it will be? D into K minus mod Y minus WL minus D times K minus mod Y plus 1, so minus 1 minus WL. Agreed? Right? So minus plus WL, so this will get cancelled. Okay? Okay. Minus dk plus dk, right? So I can write this dk minus dy. Okay? So let's write this. dk minus dy minus d. Okay? So minus dk plus dk, so this guy will cancel. Minus dy minus plus dy, this will cancel. So it will change by d. So my measure has decreased by d in D plus 1 branches. Okay? It's great. It's like roughly like d power d, which is like c power d. Okay? Okay. I will get to that analysis. Like there are trivial analysis and there are non-trivial analysis. So first let's do a trivial analysis. Okay? So this definitely decreased. Okay? Now let's look at the other side. When you decided to move him, what happened then? WL increased by 1. Agreed? This is what we did in that, right? So now let's try to see the measure. Okay? dk dy minus WL minus dk, आ रहा है सर, 2 मिनट 5 मिनट दे दो. dk minus dy WL minus 1, right? Agreed? Right? Plus WL minus 1. So at least my measure dropped both sides. I am very happy person, right? So this algorithm is, what is my branching d plus 2 to the power mu, which is like, what is mu? Is like some at most dk. So in some sense this algorithm runs in time d to the power dk. Like bad, but if we analyze correctly, this is not a good analysis. This will run in time 2 to the power big O of dk. Okay, so this is correct, but what happens when this and this is empty? How do we handle this case? I have to solve the problem optimally when there is a BL and there is a WL. Okay. So base case. So what is my base case? Here is your BL, I don't know what its size is, and here is your WL that needs to be dominated, and what is its size? At most KD for now, right? K into D1, right? Oh, I can do magic. First of all, I guess which of these guys dominate themselves. But why should they dominate themselves? I mean, if they can dominate themselves, they can better be dominated from this. So I can always assume there is a subset. Now let's write dp. Look, let me tell you first trivial solution. Okay, so these guys are going to be dominated by k people. I don't know who those people are. Let's give them variable name. What variable you like? Z1, W1, Y. So Y1, Y2, Yk. I don't know who those Ys are. Okay, but I guess for Y1, who is the set of vertices which Y1 dominates? So I partition into k parts. Like first, let's look at Y1 whichever. Maybe Y2 also dominates some portion. I don't care, but I took this. Once I gave you this partition, what is this? Is there a vertex here which dominates these guys? Yeah, check, neighborhood, done. Second, is there a vertex which dominates these guys? Done. Greedy, now I can do greedy, but this will take you kd to the power k, right? But you can do much better. Just do dynamic programming over subsets. Just do dp over subsets. Then you can do in 2 to the power big O of dk. For every vertex right family is universe. I mean, come on, this is nothing but 2 power n set cover, right? What is your universe? Universe is this, right? Your universe is this, right? For every vertex, right? So don't you know 2 power n algorithm for set cover, right? So what is my universe? My universe is WL, which is of size dk, right? And for every yi, I write the set of guys which he dominates, right? Now you can do like set cover in 2 to the power universe size, right? So 2 to the power dk algorithm. So you have to do something. Here's an algorithm for doing dominating set on D-degenerate graph using branching. Okay, so exercise. Here's an algorithm. Please, I only told you d to the power dk algorithm. Please analyze this and get 2 to the power big O of dk. See what happens. In first d branches, measure decreases by d. That's a lot, right? So for example, forget this. If I had t mu d times t mu minus d, then this recurrence will be d to the power mu over d, roughly. This is what it will be, right? And d power 1 over d is maximized for d equal to e. Since d is integer, it will be 3 to the power mu. So that is what you have to use, right? Because in every branch, and there is one branch where you lose only a little, but you can still compensate. I mean, you should know these little tricks. Okay.